Okay.
So let me continue on, and thank you, everybody. Thank you for your patience. Again, the recording of the presentation material will be made available to you after the webinar through a follow-up email. I also encourage you to fill out the survey at the end of the webinar to help us improve our webinar sessions and perhaps how to avoid these technical issues I realize. My name is Hector Lara, Product Line Manager for the Dimension AFM products at Bruker. Presenting the technology overview is Teddy Huang, Senior Application Scientist at Bruker AFM Unit. Dr. Teddy Huang is a Senior Application Scientist at Bruker, leading the development of AFM-based nanoelectrical and electrochemical modes. He obtained his PhD degree in physical chemistry from Emory University in 2012. His PhD research was focused on interfacial charge transfer dynamics in energy conversion systems, including photovoltaics and solar fuel generating devices. After his graduation, he moved to Caltech and worked with Professor Nathan Lewis as a postdoctoral scholar, where he investigated the semiconductor and metal interfacial structure using AFM nanoelectric and nanoelectrochemical measurements. As of today, he has published 43 peer-reviewed articles with more than 2,000 citations and having a Herfindahl index of 20. We are very pleased to have Dr. Huang in our technology team. Dr. Huang, if you would please proceed with your presentation.
Thank you. Thank you, Hector. So, hi everyone. So I'm here today to show you some new products about the scanning nano-EC, nanoelectrochemistry, and nanoelectrical measurement in liquids. And all these new features are enabled by the Nanoelectrode probe. And here is the outline. So last year, when the initial release of this Nanoelectrode probe and together with the PeakForce SECM, I gave a webinar at that time. You still can find it online. And for today's webinar, I'm going to more focus on the update of the PeakForce SECM. And later, I will show you the new invention from the Bruker, which is force volume SECM. And more importantly, I'm going to show you a totally new suite of features, which is nanoelectrical measurement in liquid. And here, I'm not talking about the traditional thin liquid layer or partial submersion of the probe. I'm presenting to you nanoelectrical technique that allows you to immerse the whole probe and your sample together into an electrolyte solution. Indeed, the development of these new techniques is an excellent example of success from collaboration. And this is a list of our collaborators and the related applications. As you can see later, many results presented here today were from these collaborations, and some slides are even directly contributed from our partners. After 1 year of release, this product is very popular today. They have been enabling many novel applications in different research areas. And this is some related publications after only 1 year. And I know at this moment, there's some other manuscript in preparation or under revision. And you will see some unpublished results later in my talk. So let's get started from the key component, which is the Nanoelectrode probe. The probe was prepared from microfabrication, and this is to guarantee the high batch-to-batch consistency. And the conical tip is fully insulated, except for this platinum tip apex. And this tip apex has an end tip radius about 25 nanometer and a height about 250 nanometer. And as you can see here, an embedded conductive path runs between the tip and the base. And this is for electrical conduction. And the whole probe is encapsulated in glass. And first, this multi probe is relatively big, as you can see from the picture. And the packaging also have design grooves. And both of these are for ease and safe of handling. Second, the probe is chemically compatible with a wide range of EC conditions, for example, for battery solution. Third, the insulation scheme allows current flow only through the tip apex during the measurement and no leakage elsewhere. And the conductive path technique greatly reduces the strict capacitance and some parasitic chemical reaction. And this makes the probe ideal for both scanning electrochemical microscopy, and also nanoelectrical liquid imaging. And this is some basic easy test of the probe. As a nanoelectrode, its cyclovoltammogram has an S shape, and this is characteristic for nanoelectrode. The diffusion limiting current at this condition is expected about 200 picoamp. And this CV so negligible leakage and capacitive current. The probe is really robust for handling, and it's also chemically stable. For example, these two curves, these two CVs would result before and after a sequence of handling and EC measurement as shown here. As you can see, there's no degradation on the performance. And this is another example. And these are 50 CVs captured continuously and plotted together. And you can see they're all identical. Amperometric test is another way to test the probe for stability test or for noise test. And this is a test, and you can see that the time window here is 2 hours. And as you can see, within these 2 hours, the current is really stable. And if you're zooming in the half an hour section, you can see both the noise level and the drift is in the sub-picoamp level. So the steady state diffusion limiting current I showed in the previous slide is a result of the steady state diffusion structure of the nanoelectrode probe. The thickness of this diffusion layer defines the spatial resolution for EC imaging in SECM. For this probe, the console simulation shows a thickness of less than 100 nanometer. So when a nanoelectrode is away from a substrate, it has a steady state current resulting from the constant diffusion of the redox species from the bulk to the solution, from the bulk solution to the tip surface. But when the tip is approaching to an insulating surface, this diffusion will be gradually blocked, and the tip current, of course, will decrease accordingly. On the other hand, if the substrate is active to regenerate the reactant, it will create a positive feedback, and the current will increase. And if you plot the tip current versus the tip sample distance, and now we have the very popular approach curves. For our nanoelectrodes, as you can see from the results of experimental and the simulation results, they are consistent with each other. And this demonstrates that the tip current truly coming from the active tip apex and no leakage current elsewhere. And one can also see that changes in the tip current mostly occur within 150 nanometer. And this is also consistent with the diffusion layer structure, and this is guarantee the high spatial sensitivity for EC imaging. So think about that. When the substrate surface is not insulating, but either not very conductive, and we can expect the resulting approach curve will fall into this region that between these two curves. And in fact, the shape of the approach curve, depending on the surface activity, is the fundamental behind the electrochemical kinetics quantification. And we're going to see more examples later. So in this section, I'm going to give you some update in the past 1 year from our PeakForce SECM. So SECM is a well-established approach for local electrochemical studies. In this technique, a tiny electrode brings electrochemical studies to micro and nano scales. For imaging, the sample surface underneath the tip impact the EC response on the tip. And we have seen such inference from the approach curve in the previous slide. The inference depends on the local properties of the sample. So heterogeneity of EC-related activities, such as active site, diffusion, permeability, and etc., can be differentiated and imaged by SECM. And obviously, the EC resolution is primarily defined by the dimension of this active tip. More specifically, as shown before, the resolution is actually depends not on the diffusion layer structure, but ultimately it still depends on the dimension of the active probe here. SECM has many applications, and as summarized in a recent review article by Professor Jenny Majero from McGill University. This is a very helpful article for researchers who are interested in micro or nano EC. For Bruker, we are trying to add all these SECM applications, SECM capabilities to our AFM platform, and together with our versatile AFM, the multi-model AFM information, we aim to provide researchers with extremely more informative and highly dimensional answers to their question they're working on. PeakForce SECM is based on Bruker's proprietary PeakForce tapping technique. And this PeakForce tapping is an of-resonance tapping mode, so that no cantilever tuning is required, which is really convenient for liquid imaging. Since it doesn't rely on mechanical resonance, it is robust when imaging in a changing environmental condition, such as if you have fluctuation in liquid volume or temperature. The first set point in this mode is the maximum force or peak force during every tapping cycle. The sinusoidal ramping allows very soft tip sample interaction, and so low imaging force is routinely used. And this is really good for fragile sample and high resolution imaging. And if you look at the tapping in terms of the Z position, and we're essentially performing a triggered force curve at every tapping cycle. From the real-time capture and analysis of these fast force curves, we can extract quantitative nanomechanical information at a normal AFM imaging speed. During each tapping cycle, as shown on this plot, the probe in contact with the surface with a user-defined duration. If you have a fast electronics, we can also capture some AFM signals during the contact. For example, as shown here, some electrical signals during contact, like conductivity mapping. And actually, this simultaneous nanoelectrical capture is the physics behind the PeakForce tuner and advanced conductive AFM technique that we are going to see several times later. Today, PeakForce tapping is a really popular mode, and it generates several peer-reviewed articles every day. It has been integrated with many other advanced modes for multimodal imaging. And showing here is it's a small collection of its application examples, from atom to devices, from atomic flake to complex structure, from extremely soft material to hard surface, and etc. And this is a scheme of PeakForce SECM and another PeakForce enable mode. And in this mode, the Nanoelectrical probe is part of the EC system and is used for AFM imaging at the same time. Let me bring up the again. During imaging, the probe follows the interleaved scanning pattern, and in this pattern, the PeakForce AFM information is captured in the main scan. The intermittent contact nature of PeakForce tapping during the main scan also allows the capture of the tip contact current. And this contact current holds lots of information, such as surface conductivity, and we're going to see from some example later. During the leaf scan, the tip follows the surface topography, but maintain a constant leaf height. And during this leaf scan, the EC information are captured. And this interleaf scan maintain a constant distance tip from the sample surface, regardless of the surface topography. It's an advantage from AFMs, and this is very different from traditional classic SECM mode. And here are the key components of the PeakForce SECM setup. The probe is loaded onto a SECM tip holder, a boot. It's used to cover the EC cell for evaporation reduction and scanner protection. The truck has temperature control function up to 65 degrees C. The probe is connected with a strain release module, and this module has a resistance selector to limit the maximum current flow. This is to protect the tip from electrical damage. We carefully design our electronics to guarantee low noise. We have also developed robust procedural recipe for ESD protection. And PeakForce SECM, of course, is fully compatible with glove box technique. And the video shown on the bottom right is an example. It captures when I run the experiment in a glove box. And this is some typical PeakForce SECM results from a pattern electrode. A 25 nanometer thick nitride pattern covers onto a platinum thin film, and later we'll see that this sample is going to be used for several other tests. In the EC environment, if you look at the adhesion map, you can see that the platinum is twice adhesive compared to the nitride to the tip. And this is quantitative nanomechanical information. The contact current clearly differentiates different material domains. SECM current also shows positive feedback on platinum, while negative feedback on the nitride. The contrast between these two domains on the SECM current, as you can see from this line plot, and this is plot according to the lip height. And when I increase the lip height, the contrast is gradually lost. And this is consistent with the diffusion nature of the chemical in the solution. And the one thing I want to point out, as you can see here, the changes mostly occurs within 100 nanometer lip height. And this is again confirm the compact structure of the diffusion layer. And this is a real application example. And this example has been published on nanotechnology recently. In this example, the PeakForce SECM is used to characterize a surface defect on an HOPG electrode. The submicron defective region is only about 0.4 nanometer higher than the surrounding terraces. However, this region, this defect has a very different mechanical properties, and its SECM current, which is the EC activity, is also very different from the surrounding. And as you can see, the SECM current is about 10% lower than the HOPG terrace. This is another example that recently published on Cancer Scan. The sample here is a silicon electrode, and with a platinum catalyst nanoparticle deposited on the surface, and the deposition is electroless deposition. It's very interesting that in air we don't have any problem to image this sample, but when you put this electrode into aqueous solution, it doesn't matter it's water or some electrolyte. The particle is found to be only loosely attached to the silicon substrate. But we managed to do that with PeakForce tapping, even though contact mode tapping mode is very, very challenging and even impossible. The contact current here is actually directly related to the interfacial conductivity, and I have going to show you more detail later. And the SECM current here, which is the electrochemical current from the particle, depends both on the interfacial conductivity and also the EC activity. The one thing I want to point out, as you can see, there's 4 particles here. This is about 120 nanometer particle. They sit next to each other, and we can differentiate them clearly on contact current map or the SECM current. So I'll come back to this slide when I talk about the conductive measurement in liquid later. Now let's move on to the new invention by Bruker that we have recently, which is Volume SECM. As I mentioned previously, approach curve is a very important element for electrochemical kinetics quantification. In literature, you will find lots of examples like this. There are several approach curves from several locations of the sample surface, and this approach have different shape is because this location have different EC activities. Naturally, it would be highly desired if we can achieve a whole map of approach curve, that is approach curve array and approach curve on every pixels. And now, today, Bruker make this possible through the integration of AFM SECM with force volume. So what is force volume? Force volume linearly ramp the tip towards the surface until it hit the user specified force, and then ramping back again, all the while recording the force between the tip and the sample. This is a very powerful tool for looking at mechanical properties, but it is limited in speed. As you can see on the video on the right, it is a real-time video of a traditional force volume technique. On the other hand, PeakForce tapping was developed to overcome the speed issue while allowing imaging with low force, high stability. However, PeakForce tapping is too fast for a regular, low bandwidth, commercially available potential step to resolve the real-time EC data during the sinusoidal probe ramping. In this regard, the force volume works nicely because it's slow, but we have more control. And force volume also allows ramp and hold functionality that allows you to hold the tip on the surface to do something else, and you can see more example later. By the way, I want to point out that today, Bruker's fast force volume can now run really fast, getting to 0.2 kilohertz, which is close to the low-end speed of PeakForce tapping, as shown on the real-time video on the right. And showing here is the force volume SECM. In this mode, the force curves are naturally captured by force volume. During the force ramping, the tip current is simultaneously acquired, and the SECM approach curve was generated. And put together, we have force volume SECM. We have all the information that PeakForce SECM can have, while as more, we now have spatially and temporally resolved EC data. This immediately allows us to have EC activities in function of distance to sample surface at the accuracy of sub-nanometer and in every pixel. This is really three-dimensional electrochemistry. With all the collected spectra, we can have a movie to show you the dynamic change of the surface activity as tip sample distance. And what I'm showing you here on the bottom right, 1024 image, and this is all along the sliding the spectrum on the top. Compared to traditional AFM imaging modes, any mode based on force volume generates way more data, and this is towards to the concept of big data. How to decipher the data cube to extract meaningful results really requires some creativity, even some art. And here is another example of force volume SECM. The sample is a gold electrode with an insulating flake on it. The positive and negative feedback are clearly seen on gold and oxide surface, respectively. Force volume is much more striking for data visualization. From the spectrum on the top, we can also see the contact current and how the nanoelectrode behaves when the contact is breaking. Density plot is a very popular approach to recognize the most outstanding phenomena from a statistic population. In force volume SECM, we generate a large population of spectrums. For example, here I showed you 1024 curves in this case. Then density plot help us to identify which EC activity are most commonly present. For example, in this electrode, the two curves with darkest colors represent the oxide and the gold region. In between are approach curves captured when the tip is at the edge of the oxide and where we have both positive and negative competing feedback from gold and oxide, respectively. With the ramp and hold function that I mentioned previously, we can hold the tip on the surface for other purposes. For example, for making nano contact to micro or nano domain when it is impossible to make an electrical connection to that region as usual. This slide is a proof of concept, and next slide I will show you a real example. The plateau of the force curve indicates that the tip is in constant contact with the sample surface at constant force. Here is 10 nanonewton. During the contact current is captured. In this example, the sample is a platinum electrode covered by a nitride pattern. We did not apply any potential to the sample surface. However, when the tip is in contact with the platinum region, then the whole platinum electrode, the bulk electrode, is electrically connected. And now you can see a huge electrochemical reaction current here. This is actually a saturation current. But the connection, the nano contact, the quality of the nano contact really depends on the surface conductivity. If I have some surface contamination or something that in between the tip and the sample surface, then you will see the current is going to change. For example, if you compare the black and the sine curve here, and if you zoom in into this plot, when I put the tip onto the nitride surface, and now this electrical connection is disconnected, and now I can only see the background current from the platinum tip itself. And interestingly, of course, during this kind of like a probe ramping, you can also see the positive and negative feedback at the same time. And what I'm going to show you in this slide is an excellent example about holding the nanoelectrode probe on a sample surface and measure the in-operando properties like in-operando surface electrochemical potentials. And this slide was contributed directly by Professor Shannon Boucher and his graduate student Michael Newlist from University of Oregon. This work is related to using sunlight to split water into hydrogen and oxygen, that is solar energy, to chemical fuels. Here they are looking at the water oxidation half reaction to generate oxygen. The semiconductor photo anode is alpha iron oxide coated with carbophosphate catalyst. Michael placed this photoanode into a photoelectrochemical cells that he designed. The photoelectrochemical cell allows simultaneously for AFM imaging, nano-EC scanning, and photoillumination, and as this is shown on the scheme here. In this work, Michael studied the interfacial charge transfer processes on this photoanode. The role of the catalyst on the semiconductors, like here carbophosphate on alpha iron oxide, is largely debated, with some saying that water oxidation takes place at the semiconductor surface. To understand this, you really need to know the potential of the catalyst in operando to understand what the catalyst is really doing. Using nanoelectrode probe, Michael demonstrates localized potential measurement on the catalyst surface, and this provides a direct measurement of the photo voltage. Michael could then show that the catalyst voltage is the same whether it is on a conductive ideal substrate or an iron oxide semiconductor substrate. And this proves photogenerated hole transfer from the semiconductor to the catalyst, and water is oxidized by oxide in the catalyst. This work has been accepted by Nature Energy and will be available online soon. Indeed, the Boucher's group has done quite some work on AFM-based nanoelectrochemistry in the past year. I would really encourage you to read their recent papers. Besides this Nature Energy one, you will learn a lot from Michael about EC, AFM, SECM, and how to design a photoelectrochemical cell for AFM studies, and etc. All right, let's move on to nanoelectrical liquid measurement. Today, Bruker provides a versatile array of electrical techniques for a multitude of applications. And this table shows the properties that one can measure from corresponding Bruker AFM modes. Basically, anything can be measured microscopically, as such by hand-carried multimeter. It can be measured by a AFM mode as well on the nanoscale. And PeakForce tapping, of course, can be integrated with most of these nanoelectrical modes. And I mean, integrating with the PeakForce tapping will give you a lot of advantages. For example, it will help you improve the tip lifetime with hard samples. It will decrease sample wear with soft samples. And together, it will improve the resolution due to the sharper tips and less sample damages. And this is allowed to measure some sample that previously AFM impossible. And this is an example. This is a PeakForce tuner measurement, PeakForce tuner example on some delicate sample, and this is the this is polymer nanotube composite. And of course, AFM characterization for this sample is impossible in contact mode. But PeakForce tuner very nicely resolved the fine nanophase separation of the polymer as well as a signature of the embedded carbon nanotube in the electrical current imaging. And high-quality correlated topographic, mechanical, electrical signals can be obtained simultaneously. Nanoelectric technique has, as shown in the previous slides, has been nicely adopted and widely used in air. However, lots of applications today require running such measurement in electrolyte solution. For example, if you are working on lithium-ion battery, you would be very interested in the real-time development of the SEI layer. And indeed, we would like this layer to be ionically conductive, electrically insulating, and mechanically elastic and robust. And due to the nature of this layer, it will make more sense to study all these properties simultaneously in situ. The PeakForce conductive AFM performed in a battery solution will be ideal. And as for bio studies, we often talk about two things. One is bioelectricity. Second, a living organism is generally an electromechanical system, that is, mechanical response results from electrical stimulation or vice versa. All this occur in a biological environment, that is, in a solution with an electrolyte concentration of about 150 millimolar and at a certain pH. And for the example I showed you before about the platinum nanoparticle catalyst, the interfacial conductivity is a critical factor. Indeed, for any EC process, the interfacial conductivity is a key factor to determine the overpotential that needed for driving a desired reaction. And this is the input energy penalty from the IR job at the interface. A direct measurement of the interfacial conductivity would be more desired than through some indirect measures that require assistance from simulation. All these studies require nanoelectrical measurement in liquid. However, today, it is still not feasible to implement this technique in liquid. This comes from the challenges as shown here. First, the measurement generally require the full immersion of both the conductive probe and the sample in liquid. Making this without electrical shorting, without liquid spilling, and without chemical corrosion is not trivial at all. In addition, unwanted electrochemistry can dominate your signals. Other background contribution can come from the straight capacitance. To avoid these persistent contributions, an insulation scheme is really required to achieve local signal with high signal-to-noise ratio. And the multi-nanoelectrode probe lesson that we have learned from the SECM operation as discussed previously, and the existing sensitive electronics for nanoelectrical measurement in air altogether enable us to make nanoelectrical measurement in liquid possible. Let's start with some example from the conductive AFM. And this is an example of PeakForce tuner measurement in organic solvent DMC, and this is done in glove box. And the sample is the one that we used before, but this one with intentionally under etched, leaving only partially exposed platinum, but there was some nitride on the platinum region. And DMC solvent is a solvent that frequently used in battery research. From this measurement, as you can see, we clearly differentiated exposed platinum on the current map. The heterogeneity of the surface conductivity is also confirmed by the IV spectra at different locations as labeled here. When it's on the nitride surface, as shown on this location number 3, we only observe negligible background current. The background noise is better seen on the line plot here on the bottom right. When as you can see here, only sub-picoam noise level are achieved. Compared to the organic environment, as shown in the last slide, aqueous system has other challenges. For example, it has a much smaller window for applied bias. It is also more vulnerable to contamination of unwanted chemicals like metal impurity, dissolved oxygen, alien reductants, and etc. Then we tested our PeakForce tuner in 1 molar KCl solution, and the KCl shown here is used upon receipt. We didn't do any purification. And this is to check the quality of the electrical signal when the DC bias is applied to the conductive solution. As you can see here, we can differentiate exposed platinum surface from the nitride surface. And on the nitride, the persistent current from unwanted chemical reactions and the noise level are also both at the 1 picoam level. And this is another interesting study. This is related to interfacial energetics when a semiconductor metal junction is exposed to an aqueous solution. In this example, we use electron beam lithography to pattern an array of gold nanoparticles onto a silicon surface. We landed the tip on the particle and captured the IV curves. In air, we have a perfect rectifying junction as shown here. Interestingly, when this diode, when this metal semiconductor junction is exposed to water, and the diode-like behavior is completely changed. And this example demonstrates the influence of the liquid on the interfacial energetics. And this example also manifests the importance of having the system started in situ in liquid. All right, now let's get back to this example because the PeakForce SECM can also give you some information about the surface conductivity. As I mentioned, this sample was prepared from electrolyte deposition, and this type of preparation will result in highly heterogeneous interface chemistry, and then you will expect very different interface conductivity. So as mentioned previously, the contact current measured here is related to the interface conductivity. EC current on every particle, that is the SECM current, are depending on both the interface conductivity and the EC activity of the particle itself. So if you look at this correlation plot between the contact current, which is related to the interfacial conductivity, and the SECM current of the particle, you can see that when the interface is resistive, we have pretty much a linear correlation between the SECM current and with the contact current. It's because now the interfacial charge transfer is the limiting step. However, when the interface is very conductive, you will see that the SECM current is pretty much the same. It's because now the EC activity can be compared. And this is a forced electron redox couple. If all the particles are very clean, if the mass is clean, you will expect they're pretty much the same. However, I mean, as I mentioned, electrolyte deposition might introduce some contamination or some chemical impurity. And you can see that, for example, particle number 2, even though it's very conductive at the interface, its EC activity is slightly lower than the number 3. And this is also shown on the image contrast. You can see the contact current is much higher on 2. However, the SECM current is slightly lower than the number 3. All right, now let's take a look at some KPFM results in liquid. So again, we use the same sample. And of course, on the nitride surface and the platinum region, you're going to see some surface potential difference in air. And this is shown on the line plot on the right, which is correlation between the topography and the surface potential. And here we showed about 125 millivolt differences. And interestingly, in the open loop KPFM, we can also see this kind of contrast, and that's similar in water. And we also see the same thing in DMC, which is organic solvent, and we even see the similar thing in 1 millimolar KCl. However, when you go to 10 millimolar, the contrast is lost, and this is very consistent from the literature report. Okay, this is the last section of my talk, and now let's take a look at some electromechanical study by PFM in liquid, and this is related to some biological studies. And this is a slide that is contributed by Professor Zhigao Hu's student, Anyang Cui, from East China Normal University. And this project here is about high-resolution electromechanical imaging of biocompatible ferroelectric materials in electrolyte with varied concentration. The sample itself has featureless topography, where you can see very clearly different domains on the PFM phase image when we measure it in air at the contact resonance. The contact resonance in air will shift when you move to the when you do the study in water. However, we use the same frequency that we use in air, and even if it's off resonance in water, you still can see the phase contrast. If we move to the contact resonance in water, and if you look at this region, you can see that way more information that you can see compare the one on the off resonance. And it has been known in literature that the conductive environment will blur out the domain contrast. And for this sample, we also observed a similar trend. And for example, from 10 millimolar all the way to the 1 molar sodium chloride, you can see the phase contrast gradual loss. And this implication is very important. It says that electrolyte will impact the performance of the ferroelectric material. Of course, this is very important for bio applications or other energy research. Similar to the previous samples, for PPLN, a very standard test sample for PFM in air, and now on this sample, we also observed the gradual loss of the domain contrast when the increase in the electrolyte concentration. For example, in air, you can see a perfect contrast, and then this contrast just gradually go away. That when you go to 10 millimolar, it's very, you can see that, and this is better seen on the histogram plot. In air, we can see pretty much like we can see the perfect 180-degree phase contrast, but at 10 millimolar, we can barely see the contrast, and a single peak on the histogram is observed. And all these results are indeed, I mean, this slide is actually our initial studies from the PFM in liquid measurement. And at that time, we did not intentionally optimize the imaging force at the beginning. And at that time, we generally applied imaging force more than 100 nanonewton and even 200 nanonewton. Even at such high forces, the nanoelectrode probe can last for days. Of course, later on we found that the imaging force for PFM in liquid can be lower than 30 nanonewton. And this is actually one of the advantages that running PFM in liquid, because you don't need to worry about the capillary force in air that you have in air. And we have a more careful study, and more detail will be reported by Anyang Cui from Professor Zhigao Hu's group from East China Normal University. So in conclusion, in this talk, I've showed you details about our nanoelectrode probe, which is robust, high performance, and has enabled a suite of new advanced EC and nanoelectrical modes in liquid. PeakForce SECM enable high spatial resolution, EC imaging, and also multimodal capture on soft and fragile sample. For Spatial SECM, which is a new invention from Bruker, allows for improved kinetics qualification and provides 3D EC mapping through capturing a complete data cube. And finally, the PeakForce nanoelectrical measurement in liquid provides new capabilities for visualization of electrical process in solution. And this is my talk, and thank you for attention. I'm happy to take any question you might have.
Thank you, Dr. Huan. This was quite impressive as far as the data that was presented here. We appreciate that. We're very excited at Bruker using these new nanoelectrodes that are conveniently available for everyone to do their own experiments. As you can see, through collaborations, Dr. Huan has achieved some pretty impressive new studies that were not available before. So let me address some questions that have come in. Is this nanoelectrode available and compatible with any AFM from Bruker? Do you need extra fluid cell to run electrochemical experiments?
Okay. So at this moment, as far as I know, so now the Pro is only work with the icon AFM. I think maybe this is better that Hector address this question.
Yeah, I mean, I can certainly comment on it. It is correct. This is only available for icon at this moment. If you certainly, you know, we will certainly entertain any of your needs. If you have a specific Bruker AFM that you want to adapt this to, we'd have to look at your experiment and then try to understand how we can adapt it. But right now, it's only available on icon. So let me go to the other questions here. Bear with me for a second. They're coming in. I'm just running through them in no particular order, so bear with me here. Is it possible to use this probe with other imaging modes like contact and tapping mode?
Yes, I mean, so if you, if you remember the outline slide, I actually grayed out the contact mode and the tapping mode because I will only want to focus on PeakForce tapping. But there's no limitation on using the contact mode and the tapping mode. And actually, so actually contact mode I use a lot and quite often to do some interesting tests. And for tapping mode, I actually have a backup slide here. So this is actually a tapping mode. Imaging on I think this is a live cell, and I use a tapping mode in liquid, use our SECM probe, and you can see that there's no problem at all for using this tip in liquid and then do some tapping mode measurement. So yes, there's no limitation on the contact mode or the tapping mode.
Okay, very good. Where can I find more information on PeakForce Tuna and PeakForce KPFM imaging in liquid?
This is a good question. Okay, so before this product, to my best knowledge, I can only find one example about conductive AFM in liquid in the literature, and in that example, they are both actually doing they're only doing they're doing both the contact current and the SECM current at the same time because they have a redox couple in the solution. I mean, just send me an email. I can share with you with that article. Other than that, I don't have any information about the conductive AFM in literature. So that is to say that the two papers that we published, one is on the microscopy today, and second is the one on the nanotechnology, are those two that you can find. Of course, I think later on we put several more examples on the Bruker application note. So I would expect coming out more conductive AFM measurement liquid will coming out in literature. So for KPFM, there already has a lot of studies in liquid. People have done quite a lot. But it's not easy to do that because you always need some user modification, or you need to use some home build setup. And Bruker here today, just as one mentioned, in the advantage of using our solution is to help you to avoid a lot of trouble. You can use the full solution. I mean, you can put all your tip and sample in the solution all together without worrying about electrical shorting. Yeah, just send me an email and I can share with you more details.
Okay, very good. The other question is, what is the value of capacitance of the Nano AFM SECM tip in dilute aqueous solution?
Can you repeat?
What is the value of capacitance of the Nano AFM SECM tip?
Capacitance?
Yes. Capacitance.
I'm trying to understand the question here because actually the capacitance signal most of the time is something we want to avoid. Because if the tip is not well insulated, and then you are going to end up the electrical double layer directly exposed to the electrolyte, and then you are going to have a lot of background capacitive signals, and you will blur out your signal. For example, if you have a big capacitance background when you run a cyclobutanogram, your electrical signal will be really blurred out. For example, I showed you a very beautiful S-shaped curve in my slide. If you have a big capacitive background, you have a browner shade or even just really widen, and you are not going to see anything. So I'm not sure if I understand the question correctly, but you can follow me because you can have my email on my slides.
Yes, I would encourage you to follow up directly with Dr. Juan to continue that discussion. We're up against the hour here, but I will take a couple of more questions and maybe we can give them some brief answers. Can PFM be an appropriate tool to measure piezoelectric pyroelectric response in real time?
In real time? Actually, the example I'm showing here, actually, it's that different from the conventional PFM. We actually use we actually integrate with our force volume, and there you can apply a lot of dynamic change. So I didn't mention that because we are going to have something new coming up. So by saying that, yes, we can study a lot of dynamic change in liquid with this nanoelectrode using the PFM mode.
Okay, very good. And we'll have one last question. And for those questions that we do not answer, we'll follow up via email. How does the probe respond to solution with different pH levels?
So this, of course, I mean, this is I need to answer this question carefully because when you talk about pH, it's not only the pH itself, it's also related if the solution is corrosive or not. So I can give you an example. At pH 13, we know so we test a 0.1 molar KOH and have a lot of data there. The probe is pretty robust. And then we also try pH 1, and then we using sulfuric acid. And the probe is also stable for whole day, no problem. And so generally speaking, if your acid or base solution are not aggressive, the probe should be okay.
Okay, very good, Dr. Juan. I want to thank everyone for attending this webinar. Please stay tuned for future webinars, and thank you for your patience at the beginning there. Dr. Juan, thank you again. This was very impressive data that was demonstrated here, and thank you to all the collaborators. Everybody have a great day. Thank you.
Thank you.